Now let us move on to the next invited speaker, Nirit Dudovich.
Thank you very much, and I would like to thank the organizer for inviting me here. I would also like to thank Ursula Keller for a beautiful introduction into this field and really exciting results. So I will describe in my talk how we can use attosecond pulses or high harmonic spectroscopy in order to, again, record extremely accurate movies. But before starting, let me first thank my co-authors. So first, special thanks to my wonderful group at the Weizmann Institute in Israel. And also many thanks to a unique collaboration I have with Misha Ivanov and Olga Smirnova from the Max Born Institute in Berlin that actually gave me the theoretical support to this work. The major breakthrough in attosecond science in our ability to record, I think, phenomena with attosecond accuracy is truly based on two fundamental steps, two fundamental breakthroughs. The first is the ability to produce optical pulses with less than 1 femtosecond duration. And this is a crucial step because it really opened up this entire field that we call now attosecond science. And the second step, as Ursula already described, is the ability to apply those pulses now in order to perform measurement. We apply an attosecond pulse or attosecond pulse train in order to initiate or probe a fast-evolving process. And in the past 2 decades, we have been witness to many and beautiful experiments that show the ability to resolve for the first time electronic wave function, how they evolve on their own natural time scale. So now we can watch those wave packets and how they evolve with a resolution of less than 1 femtosecond. We can ask ourselves, what is the fastest movie that one can measure? What are the basic limitations in such a measurement? Well, if we use the attosecond pulse as a pump or a probe, then the answer is quite simple. The resolution is simply dictated by the duration of the attosecond pulse. And currently it is set at few tenths of attosecond. But as we already heard by the previous talk by Ursula Keller, some phenomena, very fundamental phenomena, evolve faster than even few tenths of attosecond. And therefore the question is this the main limitation? Is this truly the basic limitation, or can we break this limit? In other words, can we record phenomena that evolve faster than even the shortest available attosecond pulse? Ursula gave one beautiful example of how we can break this limit. In my talk, let me show how we can do that by stopping exactly at this point right after the production and take then one very important step backwards. So I will show that if we zoom back into the generation mechanism itself, we realize it provides us with unique insight into many strong field phenomena, and in fact, it can serve as an extremely accurate measurement that provides us wonderful resolution. So how do we produce attosecond pulses? The basic mechanism is now very well established. It has been studied during the past 2 decades, and really the pioneers in this field are Paul Corkum, who explained the basic model, and then Levenstein, who gave a very accurate description, quantum mechanical description of how the production process evolves in time. The basic mechanism can be explained as a 3-step story. At the peak of the laser field here, the Coulomb barrier is suppressed, and an electron can tunnel out. Once the electron is free, it is accelerated by the strong laser field, accumulate very high kinetic energy before it may recollide with a parent ion. And recollision now leads to the emission of optical radiation in the X-UV, and today approaching even the X-ray regime, where the frequency of those photons are dictated by 2 main parameters. It is dictated by the ionization potential and kinetic energy accumulated by the electron. But really the most important aspect of this mechanism is the fact that it evolved during less than 1 optical cycle, and therefore we have the emission itself will have sub-cycle or attosecond duration. Now, in most laboratories, including mine, we have a multi-cycle IR field that drives this process, and therefore we repeat the story again and again and again. We do not generate a single attosecond pulse. We generate an attosecond pulse trend where the pulses are separated by half of the laser period. So this is a periodic structure in time transferred to be a periodic structure in frequency, and this is the well-known high harmonic spectrum where each frequency component is associated with an odd number of the fundamental frequency. Okay, so we understand this three-step mechanism. It has been extensively studied over the past 2 decades. We can also think of it as a very simple pump probe measurement, a very similar measurement to the one that was described by Ursula in the beginning of her talk. Tunnel ionization in some atomic, but in many molecular systems, leaves behind a non-stationary state. As the electron tunnels out, it really initiates a whole wave packet. And this wave packet can evolve very quickly during less than 1 optical cycle. So this is a pump. It's an extremely accurate pump. Then when the electron accelerates with the laser field, we can think of this acceleration as the delay line. And finally, as the electron recollides, it probes the evolved wave function and map information into the optical frequencies that we measure in the lab. So we have ionization pump, then a delay line, recollision probe, and the output of this experiment is the high harmonic spectrum. And indeed, over the past decade, many people have used this idea in order to look at fundamental strong field phenomena with extremely high resolution. So this is wonderful because all we have to do now is to measure the high harmonic spectrum, and it contains everything, in principle. In principle, we can use it in order to record how electrons rearrange upon ionization, how charge is being transferred in different molecular systems. But truly, before we can reach this dream, I think first we have to see how we apply this technique in order to observe very fundamental strong field phenomena. And in my talk, I will focus again on field-induced tunnel ionization. But let me ask the following question. We have the pump, we have the probe. What are the different frames in our movies? How do we scan the delay line? Naively, the electron can be born at each point along the optical cycle. If it is born late within the cycle, at this point it returns quickly after, but with relatively low kinetic energy. So this is energy, this is point of ionization, point of return. So we have here pump, and then probe, return with low energy. If the electron ionizes slightly earlier, it will have a longer trajectory, but it will return with higher energy. In other words, the earlier the point of birth, the later will be the point of return, and therefore the higher would be the energy. And this is, of course, true up to a certain point, up to the cutoff frequency. Well, eventually the field decelerates the electron, and the instantaneous energy reduces with the trajectory length. But really, the beauty of this very naive, very simple picture is the mapping it provides us between trajectory length and energy of return. So these are the different frames in our movies, okay? And we can associate each harmonic component with a single frame, with a single pump probe delay time. And let me now show how we can use this approach, again, to revisit one of the most fundamental strong field phenomena, also described by Ursula, field-induced tunnel ionization. Field-induced tunnel ionization is truly the starting point for attosecond science, right? It is the basic process that enables us first to generate those harmonics, to perform attosecond scale experiment. It also led to many other beautiful observations as electronolography, double ionization, and the atto clock that was described before. How do we understand this mechanism? Well, we can use a very naive and simple model to describe it. And in this model, tunneling evolves adiabatically. In this model, let's consider the barrier and how it follows adiabatically the instantaneous field intensity. This is, of course, an approximation, but it provides us with very good intuition. So within this simple picture, we understand that if the electron tunnels at the peak of the laser cycle, here the barrier is suppressed and tunneling probability is relatively high. A few hundreds of attoseconds later, the field drops to 0, the barrier lifts out, and tunneling probability completely shuts off. So this entire mechanism must evolve within a tiny fraction of the optical cycle. It's an extremely highly nonlinear process, and it must evolve within few hundreds or a few tenths of attosecond. And let me just mention the pioneering experiment that showed that indeed tunneling as a sub-cycle mechanism came from the group of Max Planck, headed by Ferenc Krauss. They were the first to show that indeed field-induced tunneling is not a cycle average mechanism. It evolved during less than one optical cycle. And when I first did my first step in this field and started to think of field-induced tunneling, I realized that there are several fundamental and very challenging for experimentalists to ask. Well, we can ask, what is the tunneling time? And this very important question was already beautifully addressed by Ursula. We can ask the following question: can we resolve the moment in time in which those electron trajectories appear in the continuum? In other words, can I measure the effective fraction in the optical cycle in which ionization occurs, or the electron starting point when it starts to interact with a strong laser field? And we can also ask, can we follow how the barrier itself changes in time? In other words, can I watch how the instantaneous tunneling probability changes within the optical cycle? Mathematically, we can associate the last two questions with two mathematical numbers. The moment at which the electron appears in the continuum is associated with the real point of tunneling ionization time. And let me just emphasize, this is not the same time that Ursula measured. This is really the starting point of those electrons that appear in the continuum. The instantaneous probability is associated with the same time, but now it's the imaginary component. Okay, so what is the required resolution if one wants to measure, one tries to answer those questions? Well, the duration of the optical cycle in the IR regime is few femtosecond. Tunnel ionization, which occurs within a fraction of this cycle, must evolve within few tenths or hundreds of attoseconds. So if we want to answer those questions, we understand that we need about 10 attosecond precision. If we want to be able to follow how the barrier changes in time, how the probability changes, we need also angstrom precision. So we need a measurement that will provide us with unique combination of both attosecond precision and angstrom precision. So let me go back to the recollision experiment. Recollision by itself provides us with an extremely accurate measurement. Naively, the electron is born at the origin, right? It's born at 0 with almost 0 velocity and must return exactly or almost exactly to the same point in order to produce photons. So just by looking at the schematic figure, we already realize that we have here not only temporal resolution, we also have very high spatial resolution, because any tiny modifications of these conditions may lead to dramatic influence on the recollision probability and therefore on the output signal. Recollision that transfer really the information of the electronic wave function into photons, and those are the photons that we measure in the lab, holds an additional advantage. They really transfer the coherence of these electrons into photons. So we can use different coherent technique to perform measurement. For example, we can use an interferometer, and in the next stage of the talk, I will show how we can use this advantage. So I hope I convince you that recollision is a great measurement, and in principle, right, when we look at the harmonic spectrum, and this is something that truly excited me when I did my first step in high harmonic spectroscopy, we realized that the entire information is here. The tunneling dynamics, the acceleration in the continuum, the evolution of any whole wave packet that was left behind, and even the structure of the orbital. All this information is hidden within the broad range of frequencies that we measure in the lab. But really, I think this multiple dimension that are hidden in our experiment also set the basic limitations. We have many degrees of freedom there, right? And that's why high harmonic spectroscopy are sometimes very accurate experiments, but experiments which are very difficult to interpret. And let me just tell you that in my group, in many other groups, we have lots of data that sit on our table and just waiting to be interpreted. These are very difficult experiments to interpret, and the problem is that we have many degrees of freedom, and they're all folded into one array of frequency. So the question is, how do we decouple the different degrees of freedom? In some sense, this limitation or challenge reminds us with multidimensional spectroscopy. If we take a system with many degrees of freedom, simply resolving its 1D spectrum is not sufficient to study the entire multidimensional dynamics. We have to add more knobs into this system. So how do we increase the dimensionality in high harmonic spectroscopy? The basic limitation is the fact that these are strong field experiments. So I cannot simply change the laser parameter. I cannot simply add more fields because I may dramatically change the entire mechanism. So the question is, can we increase the dimensionality of those experiments while keeping the story as simple as possible? Ideally, what we would like to do is to apply a gate here that is very sensitive to the recolliding electron dynamics and probes the electron without changing the basic mechanism, without changing the tunneling, the return time, or any other dynamics that we have initiated. So what we require from such gate is that it has to be a weak perturbation. We want to perturb the process in a very, very sensitive way, so not any perturbation would give us an information. We want this perturbation to be, for example, a window in the ionization time. And finally, we want to be able to shift it within the optical cycle such that we can record different frames in our attosecond movie. Oh, sorry, this is mine. I'm sorry. We can think of different approaches to apply such gate. A simple one would be to add a weak second harmonic field, which is orthogonal to the strong fundamental field. Now, if this field is orders of magnitude weaker than the strong fundamental field, then it doesn't change the basic mechanism. The main effect will be a tiny kick it applies on the electron before it recollides. So it kicks the electron, and this kick can be only a few angstrom, yet it may lead to a dramatic effect. If the electron is kicked, recollision probability is suppressed, and therefore the emitted signal is suppressed as well. And now we have a very accurate knob to turn. We can change the two colors delay such that for some delays, the electron is kicked. For other delays, it returns to the parent ion and produce the maximal signal. But really, the most important aspect of this kick is the fact that it's not a DC kick. It's a time-dependent kick. So the displacement of the electron occurs only after the electron appears in the continuum, and it's very, very sensitive to the moment at which it appears, to the moment of birth or to the moment of ionization. And let me try and describe it with the following schematic figure. I'm not sure if you can see this very clearly, but let's think of different electron trajectories which are spread according to their ionization time. So those electrons are born early within the cycle. They are kicked into that direction. And those electrons, let me try and plot it, are born later and are kicked into the other direction. And only a very narrow group of electrons are able to return to the parent ion and produce the maximal signal. These are gated by a perturbation. And now if I change the two-color delay, I have the same picture just shifted. So now I select a different group of electrons to return to the parent ion and produce the maximal signal. So with this weak manipulation, I'm able to probe the electron according to the moment of birth. We performed the first experiment in helium atoms. And in this experiment, so this is energy. We resolve here up to the 79th harmonic. And here we change the two-color delay time. Okay, so this is really equivalent of shifting the gate within the optical cycle. Here the electron is kicked. The signal is low. Here it is kicked. And here it returned to the parent ion and produced the maximal signal. And we already see that this line is not flat, already telling us by looking at the raw data that there is some sub-cycle information there, that the different frames are not born exactly at the same time. They respond differently to our gate. So now in the next step, we assume that this weak perturbation is very weak, so we can use first-order perturbation theory to model it. We model the perturbative kick, and with this modeling, we can now map the information from the spectral domain through the modeling into the time domain. We map each harmonic number into its moment of birth. And these are the final results. So this is energy as a function of time, okay? And as you can see here, different trajectories are mapped into their moment of ionization. And indeed, as our intuition would tell us, those trajectories which are born early within the cycle will return with higher energy, and trajectories which are born later will have lower energy. If we compare our model to the simple classical model that has been presented by Paul Corko more than 2 decades ago, we see a clear deviation. We see a deviation of about 1/100 of an attosecond. Let me just tell you that this deviation confused us for several months. The answer, of course, is that this classical model is an approximation. It's an excellent approximation. I think it explained almost or most of the experimental observation we had in this field so far. But we have to keep in mind that it neglects many important parameters. For example, it assumes that the electron is born exactly at the origin. This is not correct. It is born at the barrier thickness at the exit point, which is a few angstrom away, but yes, it's there. It assumes that the electron is born with 0 velocity. This is not accurate as well. And if we want to be more precise, then of course we have to do a full quantum mechanical analysis. And then we find that each trajectory now is associated with a given stationary phase approximation point, and those stationary time are slightly different than the classical one. And this difference really holds, I think, the essence or the fine details of the tunneling mechanism. And this is also described by the well-known Levenshtein model. So when we compare our results to the quantum mechanical description, we have very good agreement. Okay, so far I have addressed the question, can I resolve the temporal window in which the electron appears in the continuum? In the next part of the talk, I will address the following question. Can we resolve how the instantaneous probability slightly changes as time progresses within the optical cycle? So far, our experiment didn't provide us any information about tunneling. Tunneling was a black box. Once the electron is there, we can perform a measurement. But we have no idea what's going on before it appeared in the continuum. The reason is that we applied an orthogonal perturbation that acts on the electron only once it appears in the continuum. Now, if we want to gain some information about tunneling, for example, what is the barrier thickness or what is the instantaneous probability, then we have to rotate the perturbation to be parallel to the strong fundamental field. So now it truly perturbs the electron as it propagates inside the barrier and continue to perturb the electron as it propagates in the continuum. So the electron accumulates 2 main factors. It accumulates a real phase associated with the extra phase that the electron accumulates in the continuum. But most importantly, it accumulates a tiny, tiny imaginary phase. And this imaginary factor comes from the fact that the second harmonic field slightly enhances or slightly suppresses the tunneling barrier. We perturb the barrier thickness itself. And we do that for each frame in our movie, for each trajectory. Now, the question is, how do we resolve those tiny, tiny modifications? And let me just remind you that many of the strong field experiments are very noisy. They fluctuate. Sometimes the signal can fluctuate by tenths of %. And the question is, how do we resolve the tiny perturbation factor that is accumulated here? And the answer, of course, is let's do an interferometry measurement. Okay, so let's consider the following schematic figures. We have 2 slit interferometer, and I place 2 identical barriers in front of these 2 slits. Now, if a quantum wave function propagates, it interferes, and what we record is the far-field diffraction pattern. Now, if I perturb the height of these two barriers, slightly suppress this one and slightly enhance the other one, then I change the interference, I change the interference pattern, and the main result would be, or can be, a major modification of the far-field diffraction pattern. So tiny perturbation can have dramatic effect once we use interferometric measurement. Luckily, in attosecond experiments, we have the temporal analog of this picture. So let's consider that this is a single color field, and we have here two barriers separated in time associated with the positive and negative upcycle of the laser field. The signal that emerge from these two barriers interfere, and eventually it is imprinted in the high harmonic spectrum. This is the temporal or the spectral analog of the far-field diffraction pattern we had before. Okay, so now we can unbalance these two barriers if we add a second harmonic field. For example, here we slightly enhance the barrier, here we slightly suppress it, and this unbalancing will change the interference pattern, and changing the interference pattern will lead to the appearance of even harmonics. Even harmonics, as in any nonlinear light-matter interaction, are always a signature of some symmetry breaking. They can be a signature of symmetry breaking of the medium or of the field that participate the interaction. So here, the appearance of those even harmonics indicate that we have indeed unbalanced the two barriers, and now if we resolve them, we can in fact record how this unbalance changed between one frame to another. So let me jump to the final conclusion of this experiment. So here with this recording this unbalance, we were able to record how the instantaneous ionization probability changes in time, changes between one frame of the movie to another. And in this experiment, we really zoom into a tiny, tiny fraction of the optical cycle, only about 100 of attosecond, and we can see how the ionization probability drops within this tiny window. This is really due to the highly nonlinear nature of this mechanism. We can think of it schematically as watching how the barrier lifts up. I'm not sure if you can see that. These are tiny modifications, but since the process is so highly nonlinear, it does lead to dramatic effect on the instantaneous probability. Okay, so far I've described how we can resolve the starting point of those electron trajectories that are so useful in attosecond experiment, how we can follow how the instantaneous probability changes in time. But so far the picture was quite simple because I focus on atomic system. In atomic system, everything is very clear. We have one ionization channel. The theory is quite well established. The question is, can we take it one step further? Can we go from atomic to molecular system? In molecule, the entire situation becomes more challenging because we have more than one channel that contribute. The different levels are much closer to each other compared to atomic system. And in molecule, the structure of the orbital can play an important role. So let's consider the three upper orbitals in CO2 molecules. They're not that far away from each other. So in fact, when the electron tunnels out, it leaves behind a wave packet. There are several channels that participate here, and the electron initiates some wave packet, a whole wave packet, that beats very quickly during the optical cycle. We can think of this experiment as equivalent to an interferometer, right? When we record our harmonic spectrum, we have no clue where the signal came from. This channel cannot be directly distinguished, so we have an interference between them. And in some spectral points, this interference is constructive. In other points, the interference is destructive, and this destructive interference may lead to a very, very clear minima that we observed several years ago. In this point of the minima, we can think of it as the point where the electron returns exactly at the zero of the beating pattern. And now, once we have understood the contribution of multiple channels, I think the entire field of high harmonic spectroscopy became more interesting. And one of the questions that I asked myself at the time is, can I resolve ionization dynamic from more than one ionization channel? Naively, I would say no, because those channels eventually should ionize more or less around the peak of the laser cycle, right? The fraction of the optical cycle where ionization occurs is more or less the same. Okay, so let's look at the following description, and let's consider now ionization from the upper orbital, and I consider here one trajectory with ionization time t0. And now I turn on the kicking mechanism. Let's kick this electron, and this is what schematically we expect to observe. Here the electron is kicked, here it is kicked, here it returns to the parent ion and produce the maximal signal. We can apply the same kicking mechanism on the deeper orbital that is ionized slightly earlier or slightly later. It really depends on the dynamics. And what we should expect to observe is the same response with a tiny, tiny shift, almost difficult to be observed. And there is a tiny shift because the ionization time is slightly different. Okay, now the result eventually will depend on the interference between those two channels. So if they interfere constructively with zero phase shift, then what we would observe is some average response. There is no way that we can tell whether there is one channel or 200 channels here. Right? The response would be the same. However, if we have destructive interference, then this would be great, because then we take two cosine functions and we turn them into a sine function. Then the experiment takes really the derivative of the response, and what we would observe is a dramatic shift to the great response. Okay, I'm almost done. So we did the experiment with CO2 molecules. This is energy is a function of the gate position. We started with CO2 molecules aligned at 90 degrees with a laser field. Theory will tell us that there is only one ionization channel, and indeed we measure something very, very similar to the atomic response. We measure very smooth response. Okay, now as we rotate the molecule, we really turn on the contribution of the inner orbital, and this indeed leads to a dramatic shift. And this dramatic shift occurs exactly at the point of destructive interference. So we conclude for this experiment that indeed we can observe multi-channel ionization, and the reason why we can observe something is because there is a tiny difference between their ionization time. In the final experiment, we looked at xenon atoms. An experiment performed in 2011 told us that when electron ionize from xenon, it leads to electron rearrangement. There is a vacancy in the deeper orbital. So although the electron ionized from this level, the fast rearrangement leads to the recollision into a deeper orbital. And this occurs extremely fast. So again, we perform our experiment both in simple atomic system in argon, where there is only one ionization channel, no surprises here, and with xenon, where we observe a dramatic here shift exactly at the spectral point where electron rearrangement is expected to appear. Okay, so let me just conclude. I hope I convince you that recollision experiment holds a great promise. We hope in the future that will enable us to look at very fundamental multi-electron phenomena. In this experiment, we have integrated perturbation into strong field physics, and we have confirmed basic model that describe this mechanism for over the past 2 decades. We hope in the future to go to more interesting systems in which real delays are there. We hope to be able to follow how charge migrate inside molecule. This is our dream. We hope we'll get that. Thank you.
Thank you very much for the talk.